Okay, so welcome to part 1b. We're going to learn about the various ways we can denote equilibrium here and also learn a new equation. And I had to break this into two parts because this part 1 was getting quite long. We're going to have lots of subscripts here. And a subscript is really going to denote the type of equilibrium process you're evaluating. And I didn't say reaction because some of these are not necessarily chemical reactions, they're dissociation, so a process. So a process could be a state change, could be a dissociation, could be a solubility, or it could be a chemical reaction. So this is going to apply to a lot of different things. You're going to see many different types of subscripts here attached to K. The trick is to remember that large K, when you have an equilibrium scenario, that's going to be your equilibrium constant. And the subscript is going to tell you how it's being applied. So there's two things that we can see. We can see Kc and Kp, and we're going to talk about those in a little bit in this chapter. C here means concentration. So that's in units of molarity. So that would be the example that we've been doing all along, where we've had our law of mass action and we've had our equilibrium concentrations in brackets, which means we're looking at those in molarities. Kp happens when you have a gas, and this could be generally in atmospheres. So we're looking at the partial pressure of each substance. Just like here, we were looking at the concentration of each substance. These subscripts here are really indicating a process necessarily, but the units of things that you're looking at. Am I looking at it in terms of concentration, or am I looking at it in terms of partial pressure? And this obviously you would only apply if you had a gas. Other things that you're going to see with K, Keq, and this just simply means equilibrium. If you didn't already know that large K was your equilibrium constant. K, Sp, and Sp means solubility of an ionic compound. So now we can apply this equilibrium to solubility. I take an ionic compound, I drop it in water, maybe it doesn't dissolve completely, and I have some equilibrium where I have some ions in solution and some that has not disassociated. So that's another K. I could have Ka and Kb, and these kind of go together, and we're going to do this in the next chapter. This means I have an acid, and this is a base. And these are my dissociations. So I have some acid that's breaking apart into hydrogen ion and an anion, or I have a base that's breaking apart into hydroxide ion, so base dissociation. Those are all equilibrium scenarios. I could have Kw, and the W means that this is my auto ionization of water. And you don't have to know these right now, but just recognize that there's all these various subscripts here that I can apply to equilibrium. And this isn't even all of them, but this is where we'll stop right now. Describe sort of what the system is, or what that process is that I'm particularly looking at. So if we go back to Kc and Kp. So let's look at these two here. Kc we've already talked about. Kc is in terms of concentration, but now let's look at Kp. I have sulfur trioxide gas in equilibrium with sulfur dioxide gas and oxygen gas. And I could write this in terms of Kc. So my Kc for this, I could look at my concentrations of these, and I could use Henry's law to find that, right? Because these are gases. And I would have my products. I only have one reactant. So my Kc would be written this way, and this would be my equilibrium concentrations of all my substances to calculate K, and that would be Kc. And because these are gases, I can also do Kp for these. So I can also express this in terms of partial pressures because they're gases. And I'm still going to have products over reactant, and so I'm going to have the partial pressure of SO2 gas, the partial pressure of O2 gas over the partial pressure of SO3. And now I still need to take into account my coefficients. So this would be squared. This is to the 1, and then this is squared. And so this would be my partial pressures, not my concentrations, of all substances at equilibrium to calculate K. So PSO2 would be my equilibrium partial pressure of SO2. PO2 would be my equilibrium partial pressure of O2, and my PSO3 would be my equilibrium partial pressure of SO3. And so if I knew these equilibrium partial pressures, I could plug them in here and solve for Kp. Now Kc does not always equal Kp. They can equal, but they cannot equal. So there's really no, you can't say for sure if Kc is going to equal Kp. You need to know a little bit more about the chemical reaction. So you can't make that generalization. It's not quite that easy. And this equation here is going to be an important one because this allows us to relate Kc, so my equilibrium constant in terms of concentration, to my equilibrium constant in terms of pressure. I'm going to add this component here, RT delta N. So because gases are going to behave ideally, I can apply this equation here. And if I know Kc, I can find Kp. If I know Kp, I can find Kc. I need to know the temperature and delta N here. And so delta N is going to be equal to the sum of stoichiometric coefficients of products. So basically, I'm taking the sum of my coefficients of my products. So this would be 2 plus 1, right? Because there's an understood 1 here. And I'm subtracting the sum of the stoichiometric, it's a really long word, coefficient of my reactants. So it takes a lot longer to write that out than it does to calculate it. So here, my delta N for this equation here would be 3 minus 2, so delta N would be 1. That means that Kc equals, or Kp equals Kc times RT. If delta N is 1, then Kp equals Kc times RT. My pressures here must be in atmospheres because this is the ideal gas constant, and that's going to drive your units here. R is going to be my 0.08206 liter atmosphere mole K. This is where your units of concentration are going to come into play. My partial pressures have to be in units of atmospheres. My temperature has to be in Kelvin. So this has to be in Kelvin. And then this is these are all going to be, my partial pressures are all going to be in atmospheres. This also brings into account, are there any units associated with K? There are not. So K is unitless because typically your units are going to cancel out. And even if they don't, it's just by convention that K is not going to have any units. So this would apply to the partial pressures of the gases. When I plug them in here, these must be in atmospheres. If I want to use this equation here to find Kc from my Kp value. So I'd have to calculate Kp with everything in atmospheres, and then I could apply it to Kc. All right, let's do one more example. Let's say I go back to my H2 plus I2, and these are in gas, and this is an equilibrium with 2HI. My Kc for this, remember, would be my equilibrium concentrations of my products over my equilibrium concentrations of my reactants. My Kp, since these are all pressure, I can also look at Kp, since these are all in the gas phase, then that would be my partial pressure of Hi squared over my partial pressure of H2 times my partial pressure of I2. And then if I wanted to relate Kp and Kc together, my delta N here would be 2 minus 2, so delta N becomes 0. So in this case, because delta N is 0, Kp equals Kc. This would be RT to the 0. This whole thing falls out, and this is one of those unique instances where these two are equal to each other. So if my delta N, if there's no change in my coefficients, when I sum up my coefficients in my products minus my reactants, if I get a 0, then I have this unique scenario where those two are equal. So that's the only time your Kp and your Kc are going to be equal, is if your delta N is going to sum up to 0. All right, the one other thing I wanted to cover before we left today was heterogeneous equilibrium. And so at this point, I'm going to go to the slides. At this point, we've been looking at everything in the same phase. So I've looked at all of my reactants and all of my products have been in the same phase. They've either been all solutions, so I was looking at molarity of concentration, or they were all in the gas phase. So those were the two options. Heterogeneous equilibrium happens when you have a chemical reaction where now you have things in different phases. So I have gases mixed with aqueous solutions, maybe I have a solid thrown in the mix, and so not everything is going to be in the same phase. And so I can treat them differently. So one of the nice things about heterogeneous equilibrium is if I have a solid or if I have a pure liquid, generally the pure liquid is going to be in such excess. So like here, water would be in significant excess to what's happening here. So its concentration isn't going to change appreciably. So it will just fall out of that law of mass action. So I don't have to include it. So I don't have to include things that are in the solid phase and things that are pure liquids. I do have to include aqueous solutions because aqueous solutions is a solution, and so now you have a molarity associated with that, a concentration associated with it. So heterogeneous equilibrium means that if I have a chemical system and I have a solid or I have a liquid, the amount of that solid or that liquid isn't going to change appreciably when that system reaches equilibrium. And so that I'm not going to include into that whole equilibrium mass action. So for instance, if I had decomposition, let's say I look at calcium carbonate, and that decomposes to calcium oxide plus carbon dioxide gas. Now I have an equilibrium scenario, but a couple of things here. This is in the solid phase. This is in the solid phase. This is a gas. So my equilibrium constant is just going to equal to CO2 gas, because that's the only thing that's going to be present, I'm going to factor in to that equilibrium. And so it would be, what is the equilibrium concentration of CO2? So that would be my Kc. My Kp would be my partial pressure of CO2 at equilibrium. So I could write it either way. What's not going to factor in is my calcium carbonate or my calcium oxide, because my concentrations of these are not going to change appreciably. What I'm going to look at is carbon dioxide gas. So I'm only going to consider gases and aqueous phases in my law of mass action. So solids and liquids you can just ignore. So I have liquid mercury. Mercury is the one metal that exists as a liquid. Let's say I combine that with a solution that has mercury, aqueous mercury ion. Now I'm going to form Hg2, 2 plus, as an aqueous. So my equilibrium scenario for this would look at only the aqueous, only these. So my equilibrium constant wouldn't even factor in this because this is a pure liquid. And these are going to be my smaller components. And so this would be whatever that concentration is at equilibrium, that would be give me my Kc. In this case, I don't have a Kp because these aren't gases, right? So I'm only going to express this as a Kc. So Kp only applies when you have things that are in the gas phase. All right, so that is heterogeneous equilibrium. We're going to stop here. In part 2, we're going to come back and we're going to start doing calculations with these, where we are going to calculate equilibrium constants. We're going to calculate equilibrium concentrations of the substances that are in those reactions, and that's where we're going to start doing quadratic equations. All right, so I will see you guys when we reconvene then.